Hello, this is Mr. Huber. In this lesson, we're going to learn about graphing linear functions. Okay, the word function, that's a key term we're going to see coming up here in this lesson. Let's talk about slope-intercept form as an equation. And then we'll see what that means in terms of functions. So slope-intercept form, y equals mx plus b. Or familiar with that, the slope, the m, the y-intercept, the b. Written as a function, it would look like this. F of x equals mx plus b. The difference here is that we're replacing the y with f of x. That's how this is read. F of x, function of x. If we go back to slope-intercept form, how do we get the y value? The y value depends on what we put in for x, and then we calculate and get out a y value. So the y value is a function of the value we plug in for x. We can write that in function notation, and this is called function notation, function of x, f of x equals mx plus b. So whatever this is, it doesn't have to be a y. Right? We can use any letters we want. But whatever letter we put here, the value of it would depend on, it would be a function of what we plug in to the x value. So let's see what that looks like in some function notation situations here. We want to find the value of the function, so the value of the whole function, f of x equals 3x minus 15, when x equals negative 2. So what does that mean? That means we're going to take the negative 2 and we're going to plug it in to the function. So f of negative 2 equals 3 times negative 2 minus 15. That's negative 6 minus 15, which is negative 21. So when you plug a negative 2 into the function, you get out a value of negative 21. Now let's look at what happens when we know that f of x is equal to 6. So remember, that's like saying y equals 6. So we can replace the f of x with a 6. We were trying to find the value of x. We're trying to find an x when we know the output, the whole function value, is 6. So we'll replace the f of x with 6 equals 2x minus 10. And now we're going to solve this for x. We're going to add 10 to both sides. 16 equals 2x. And then we can divide both sides by 2, and we get 8 equals x. That's the value of x. So a couple different things here that we saw. Right? In this first example, x was equal to negative 2, so we're putting a negative 2 into the function. Here we know the function value is 6, so we want to find out what's the x value that will make the whole thing come out to a value of 6. So keep in mind the different way those are written and whether we're solving for the function value or finding the x value. So you should be trying some of these here. Let's find f of negative 1 for this function. Try this out and see how you do on it. So f of negative 1 means I'm going to take a negative 1 and plug it in for x, right? I'm replacing the x. The x value is a negative 1. So I'm putting a negative 1 in for the x. And then I'm going to perform my order of operations here. 2 times negative 1, which is negative 2 plus 3, which is 1. Right, the next example, f of 5, so we're going to replace the x value with 5. And that's going to be 10 plus 3, which is 13. And now in this part C, we've got f of x equals 3. So again, note the different way these are written. F of negative 1 means we're putting a negative 1 into the function. Here, the whole function value is 3. So when we solve this, we're going to have 3 equals 2x plus 3. And I'm going to solve this by subtracting 3 on both sides. 0 equals 2x. And I divide by 2 on both sides. 0 divided by 2 is 0 equals x. Right, so finding a value of the function when we know the x value to plug in, or finding what the x value would be to give us the function value, in this case of 3. Let's look at the parent linear function. It's graphed here. So we can see that y-intercept is 0, and then the slope up 1 over 1, rise 1, run 1. So slope is 1 over 1, which is just 1. And a y-intercept of 0 would give us f of x equals x. That is the parent linear function. Slope 1 and y-intercept plus 0, we don't have to write any 0. All the other linear functions are based off of this parent. Okay? They have the characteristic of this graph, and then they're changed in some way, just like offspring are changed from their parents. Okay, so there's some variations of them, but the parent graph has a y-intercept of 0 and a slope of 1. So what would that look like when we graph and compare to that parent function? So g of x equals x plus 3. We want to graph that and compare it to f of x equals x. So when we do this, let's graph the f of x equals x. So we're going to just graph this to see what it looks like. Okay, we have a y-intercept of 0 and a slope of 1. That's f of x equals x. Well, now if I'm going to graph g of x equals x plus 3, my y-intercept of 3, and I'm going to go rise 1, run 1 to get my other points, and I'm going to have a graph that looks like this. Okay, right? Y-intercept 3, and then up 1 over 1, rise 1, run 1, because my slope is still 1 over 1, and that's what g of x would look like in this situation. So how does it compare to the parent graph? We take the blue graph, and if we just slide the whole thing up, every point, slide it up 3 points, right? Take this, go up 1, 2, 3, you'd have the point right there. Slide the whole thing up 3. The mathematical terminology for that is a translation. So it's translated vertically, that's up and down, by 3. Okay. Translated vertically by 3 units. And we take the whole graph and slide the whole thing up 3. That's a translation. Translation is where you slide a graph. Now let's look at this next one. We have h of x equals 2x. Again, let's graph that parent function here quickly. So that's our parent function. F of x equals x. Y-intercept 0 and slope of 1. And now if I graph h of x equals 2x, my y-intercept is still 0. But now I'm going to go up 2 and over 1. Up 2 and over 1. Rise 2, run 1. And we've got a graph now that we can draw through those points. And that's what h of x would look like. And that is called a vertical stretch. Vertical stretch by 2. Okay, vertical stretch by 2. When I take my slope 2, I'm multiplying every value by 2. 1 times 2 to 2. Y value of 2 times 2 to get to 4. I can go on this side, okay? This is a y value on the parent function of negative 2 times 2 would be negative 4. So it's called a vertical stretch when we're multiplying with the slope in this case to get a variation from that parent function. Taking a little break from these parent functions and linear functions and function notation, who was the first athlete to be paid a salary of $1 million for any North American team sport? And running through thinking, what sport could it be? All those popular 4 major sports. Maybe you're thinking baseball or football. Well, if you're thinking football, you're on the right track, but different kind, football. The great Pele, Brazilian soccer star, joined the New York Cosmos in 1975 to get paid $1.4 million. The first athlete for a North American team sport to make a salary over $1 million. Now let's get back to some linear functions and applications of them. So here we've got a situation with a gray wolf population. And we've got a function that tells us about the number of wolves there are. W of x equals 20x plus 10. W for wolves, wx, it can be f of x, doesn't matter. It's a function of x, no matter what letter we put there. Okay, x is the number of years since 1995. So keep that in mind, since 1995. You're almost never going to plug an actual year into a function. So we're not going to plug like 1996 in here for x. We'd put a 1 in if it was 1996 because that's 1 year since 1995. So let's graph this, and then we're going to identify domain and range and figure out how many wolves there will be in 2030. All right, so first let's label our graph. So we've got x, and then we've got w of x. And I'm going to go by years, by ones on that horizontal axis. And then the vertical axis, right, we could count by 10. So it'd be 10, 20, 30, and then each successive line is 10. I'm going to skip and go by 20s there just so we make sure we've got it labeled. All right, so scale, make sure that on each axis we're consistent. So here we're going by 1s, here we're going by 10s. Fine, so we may label that. And now we're going to graph this w of x equals 20x plus 10. So what will that look like? We're going to start with a y-intercept of 10. And then we're going to go up 20 and over 1. Up 20 and over 1. And we could keep going up 20 and over 1, right, as many times as we want to, maybe to fit on the graph, and we could draw our graph through those points. Right? So keep in mind, y-intercept 10, that's where the graph goes through the y-axis. Then we have a slope of 20, that's 20 over 1, up 20 over 1, rise over run. And now we could talk about the domain for this, okay? The domain is all of the possible x values. Well, in this case, the x values will be greater than or equal to 0. 0 in the year 1995 or any year after that, but we're not going to have negative years for this situation. And then the range would be all of our possible outputs. So w of x would be greater than or equal to 10. Right? We can see here that we're starting at 10 and the y values, the outputs, are always something then greater than 10. So 10 or anything bigger than that. And now let's look at the third part of this question. Right? How many wolves will there be in the year 2030? So if we're going to find that out, we need to put a 35 into our function. A 35, so we're going to find w of 35 because that's the number of years since 1995. So 2030 is 35 years since 1995. So we have 20 times 35 plus 10. That's 710. So there would be 710 wolves in the year 2030 based on the function we have there, w of x equals 20x plus 10. One more example here of how we can apply some linear functions to a situation. We've got an internet company charging $60 for installation and $80 per month. And we've got a function that would go with that. Okay, right? They're paying $60 for the installation at one time, and then every month they're paying 80. So x is the number of months. So if it's 1 month, you pay the 80 one time. 5 months, you pay the 80 5 times. You're paying it each month. To attract new customers, they're trying to reduce their installation to $10. So now we've got an equation where we're going to have 80x plus 10, not 20, 80x plus 10. So we have an installation fee of $10. We're still charging $80 per month. So what would that look like if we graphed both of those functions? So let's graph both of these on the same axis here. We're going to have x and then f of x. Okay. So the number of months, 1, 2, 3, 4, right? We could keep going with our number of months depending on, how much we want to graph here. And then for our f of x, our cost, we might want to go by 20s, let's say. So if we're going to go by 20s here, so it'd be 20, then 40, then 60, that would be 100. Then we'll keep labeling our scale here. Right, as long as we're going by the same amount on this axis, it doesn't have to be the same as the x-axis, but we want to make sure we've got some numbers labeled there so we know what we're counting by on each axis. All right, so now if I'm going to graph, first we'll graph this 80x plus 60. So f of x equals 80x plus 60, so we're going to start at 60. $80. So 60 plus 80 would be 140 and over 1. Then it'll go up another 80 and over 1. Up another 80 and over 1. And so I'd have a function graph that looks like that. That's f of x. Okay. Then my g of x is going to be starting at 10, so that's down here, between the 0 and the 20. Up 80, I'm going to be at 90 and over 1. 90 plus 80 is 170 over 1. 170 plus 80 is 250 and over 1. Now I can draw the line through those points and have my function there. And that's g of x, 80x plus 10. And we should notice here that the slope being the same means those lines are going to be parallel. Right? Parallel lines have the same slope. So they're never going to intersect. They're going to stay the same distance apart. They're always going to be $50 apart. Right? Because this $50 difference, I'm still going up 80 and over 1, up 80 and over 1. So this is still going to be $50 difference every month. Okay? Not the cost per month, but the total for each month. So after 3 months, right, the difference in the total cost is going to be $50. After 20 months, the difference in the total cost is going to be $50 because that $50 difference at the beginning. So we can see here this whole graph was translated up 50, or if you want to look at it starting at the blue, translated down 50, depending on when you look at it. Okay, but there's a shift between the two graphs of 50 for every point where the x value is the same. So be familiar with that terminology, translation, where we're shifting the graph. A stretch, where with the slope changes, we're stretching the graph out vertically in some manner. And we want to know function notation, how we can work with that to plug values in to get a value for the whole function, or if we know the value of the function, to figure out what that input would be to get us that value.